Today we are going to learn about exploring neural network architectures, CNNs versus RNNs. We will delve into the core differences between convolutional neural networks, CNNs, and recurrent neural networks, RNNs, explore their unique features, compare their use cases, and equip you with the skills to choose the right architecture for your data and projects. Welcome to our exploration of neural network architectures, focusing on CNNs and RNNs. These powerful tools are at the forefront of modern AI, playing a crucial role in tasks ranging from image recognition to natural language processing. In this video, we'll dissect these architectures, understand their unique features and applications, and provide you with the knowledge to select the most appropriate model for your needs. Whether you are dealing with visual data or sequential information, by the end of this video, you'll be better equipped to make informed decisions about which neural network architecture to employ in your projects. Convolutional neural networks, or CNNs, are specifically designed for processing structured grid data such as images. At their core, CNNs use convolutional layers, pooling layers, and fully connected layers. The convolutional layers apply a set of filters to the input data, capturing spatial hierarchies and patterns. Pooling layers help reduce the dimensionality of data, preserving essential features. CNNs excel in image recognition, where they can detect edges, textures, and complex patterns across layers. Used in applications like facial recognition, autonomous vehicles, and medical imaging, CNNs have revolutionized how machines interpret visual data. Their ability to automatically learn spatial hierarchies makes them highly effective for tasks involving visual data. Recurrent neural networks, or RNNs, are tailored for processing sequential data where order and context are crucial. Unlike CNNs, RNNs have connections that form directed cycles, allowing them to maintain a memory of previous inputs. This makes them ideal for tasks such as language modeling, speech recognition, and time series prediction. The recurrent layers process sequences by taking the input from the current step and the hidden state from the previous step, enabling the network to capture temporal dependencies. In real-world scenarios, RNNs are used in language translation, sentiment analysis, and stock market prediction. Their ability to handle variable length inputs and retain contextual information gives RNNs a unique advantage in sequential data tasks. When comparing CNNs and RNNs, it's crucial to consider their architectural differences and data type suitability. CNNs are optimal for spatial data, excelling in tasks that involve understanding spatial hierarchies and patterns in images. In contrast, RNNs are designed for temporal data, leveraging their ability to handle sequences and maintain context over time. While CNNs are powerful for image classification, RNNs shine in tasks like natural language processing. However, RNNs struggle with long-term dependencies and can encounter issues like vanishing gradients, which CNNs are less susceptible to. Ultimately, the choice between CNNs and RNNs depends on the specific nature of the data and the problem at hand. CNNs are renowned for their strength in processing spatial data, such as images and videos. Their ability to capture spatial hierarchies and patterns through convolutional layers makes them highly effective for image classification and object detection tasks. Additionally, CNNs handle high-dimensional inputs efficiently, reducing the computational burden through techniques like pooling and dropout. However, CNNs are not naturally suited for sequential data, often requiring adaptations like convolutions for handling time series. Despite their strengths, CNNs face challenges such as high computational costs and the need for large labeled datasets for training. Understanding these strengths and limitations enables better decision-making in choosing CNNs for specific applications. RNNs excel in processing sequential data, making them ideal for tasks that require understanding temporal dependencies and order, such as language modeling and time series forecasting. Their ability to handle variable length inputs and maintain context over time allows them to capture intricate relationships in data sequences. However, RNNs face significant challenges with long-term dependencies, often suffering from vanishing gradient issues that hinder their learning capabilities. Furthermore, RNNs can be computationally intensive, requiring careful optimization. Despite these challenges, RNNs remain a powerful tool for tasks involving sequence prediction and analysis, provided their limitations are carefully managed. Implementing a basic CNN model involves setting up layers such as convolutional, pooling, and fully connected layers. The first step is to define the input shape that matches the dimensions of your image data. Then, add several convolutional layers with varying filter sizes to capture different spatial hierarchies. Pooling layers follow to reduce dimensionality and help prevent overfitting. Once the architecture is set, the model is compiled with an optimizer like Adam and a suitable loss function. Training involves feeding labeled image data and adjusting weights through backpropagation. Evaluating the model's performance on a validation set helps fine-tune parameters and improve accuracy. Key practices include data augmentation, regularization, and careful selection of hyperparameters. To implement a basic RNN model, begin by defining the architecture with recurrent layers like LSTM or GRU. These layers help maintain context and manage dependencies over sequences. Set the input shape to accommodate the length and dimensionality of your sequences. Compile the model with an optimizer and a loss function suitable for sequential data. Training involves feeding the model sequential data and using backpropagation through time to update weights. Evaluating the model on a validation set is crucial for assessing its ability to generalize. Practical tips include using Dropout for regularization, tuning hyperparameters, and monitoring for overfitting. Understanding the unique characteristics of your sequential data is key to optimizing RNN performance. Convolutional neural networks have transformed the field of image processing, enabling applications such as facial recognition, autonomous vehicles, and medical imaging. Their ability to accurately classify and detect objects has made them a staple in industries reliant on visual data. Recurrent neural networks, on the other hand, have revolutionized language modeling, powering applications like translation services, chatbots, and speech recognition. These networks excel in capturing temporal dependencies, making them invaluable in finance, healthcare, and entertainment. The impact of CNNs and RNNs on technology is profound, driving innovations and improving efficiencies across sectors. As these architectures continue to evolve, their potential to solve complex problems and create new opportunities remains vast. Selecting the right neural network architecture involves a careful assessment of your data type and application-specific needs. For tasks involving spatial data like images, CNNs are generally the preferred choice due to their ability to capture spatial hierarchies. For sequential data, RNNs are optimal, thanks to their capacity to manage temporal dependencies. Balancing the strengths and limitations of each architecture is essential, as is integrating best practices such as data preprocessing and model optimization. Future-proofing your model involves staying abreast of advancements in neural network technologies and being open to integrating hybrid approaches that combine the best of CNNs and RNNs. By understanding the intricacies of your data and goals, you can make informed decisions on the most suitable architecture for your project. In conclusion, we've explored the fascinating world of convolutional and recurrent neural networks, understanding their unique architectures and applications. CNNs, with their strength in processing spatial data, are unrivaled in image-related tasks, while RNNs, with their prowess in handling sequences, excel in language and time series applications. Choosing the right model hinges on a clear understanding of your data and project requirements. Implementation insights emphasize the importance of optimization and best practices. As you continue your journey in neural networks, keep exploring, experimenting, and learning. The potential of these architectures to transform industries and innovate solutions is vast, waiting for you to harness.